In 1.5, I'm sorry, 10.5, we're going to be using polar coordinates to find the area of a region, the arc length of a curve, also surface area once we rotate about an axis. So, your homework for 10.5 is right here. It's only the stuff that's really necessary. Now the area of a circle, let's break this down. The area of a circle is pi r squared, but you can rewrite that as 1/2 2 pi r times r, where you're looking at the actual area of a triangle, but where, because it's 1/2 base times height, but 2 pi r is the arc length. So r theta is always the arc length of a sector of a circle. So this length right here is r theta. So if you look at this little piece of a circle, your radius is here. This is r theta, and the area of that near triangle, remember, if you break the circle down into an infinite number of sectors, then this is effectively a straight line. So the area of a circle can be written as the sum of areas of triangles. This is the area of a single circle, but you see a full circle has 2 pi for the theta. So what you're doing is you're taking this area that you're looking at and you're breaking it up into sectors. And you can treat each of those sectors, there's an infinite number of them you're going to be adding together. You can treat each one as a triangle. So looking at the area bounded by this curve r of theta on the given interval, you're going to have 1/2, and your theta from the area of a sector over here is the d theta and your limits together. So that's your theta, and there's your r squared. So 1/2 integral of r squared d theta, and you're good to go. Okay, let's try an example. We have the equation r equals 2 sine 3 theta. Because theta is being multiplied by an odd number, you know that there's going to be 3 petals. But we want to find the area that's bounded by just one of the petals. So the easiest way to do this, the first thing that you have to do, is to find the angles that begin a petal and the angle that ends a petal. So from the beginning to the end, we're going to go out from 0 and back to 0. And when we put down, just start writing down your thetas that you want to check, and you see that we get, well, for 3 theta, the sine of 3 theta is going to be 0 at 0 and at pi. And then when we divide by our 3, that gives us our limits for our integral. At 0, we started at 0. We rotated through to pi over 6, and we went all the way out to the largest value that 2 sine of an angle can be, out here at 2. And then as we rotated from pi over 6 to pi over 3, we went back to 0. That gives me one full petal. Now we can integrate from 0 to pi over 3 and do the entire thing, or we can cut that guy in half. This would be pi over 6, integrate just half of it, get half of the area, and then double it. And that's what we usually do in this case. So we're going to double the area of 1/2 the integral from 0 to pi over 6 of our r squared. So once you square it, this becomes a 4. I can pull that out. The 2 and the halves cancel. And we're going to be integrating sine squared, which we have to use a power reducing formula for. So we get 1/2 times 1, sine makes it minus, and it's always cosine of twice the angle. So now the 1/2 can come out and make that a 2, and we're just integrating 1 minus the cosine, which is going to give us theta minus the sine with the adjustment of the 1/6. And I'm assuming that we know how to do that. That was a few tests ago. So actually, it was last semester, so there you go. So plugging in the pi over 6, we just get pi over 6 here, but when we multiply that by 6, we get the sign of pi, which is just 0. So when we plug in the pi over 6, we're going to get pi over 6. Plug in the 0, everybody's a 0, and we end up with twice pi over 6, which gives us pi over 3. All right, let's try this one. Find the area enclosed by r equals 3 cosine. Now, if you've practiced your graphing, you know that this is a circle that is centered along the x-axis because it's cosine. We start from 0 here, r is 3. As we rotate to pi over 2, we've gotten the whole top of the circle. So I can integrate from 0 to pi over 2 and double the area. So doubling the area, 1/2 integral of r squared from 0 to pi over 2. That gives me a 9 cosine squared. Power reducing, there's the half that I pulled out. Integrate. When I plug in pi over 2 right here, I'm doubling it. That makes it sine of pi, which is 0. Plugging in the 0, we get all zeros, and my answer is the pi over 2 times the 9/2 out front, and I get 9 pi over 4. Do you see that it's very important that you're able to graph these before you start trying to work the problems? Okay, the area enclosed by r equals 9 minus pi. Now this is a really weird one. It's a convex lemacon. And what happens is it's not a circle. It's longer this way than it is wide, and it's shorter this way. And if you look at the chart in your book, you'll see graphs of this form. So what I need to know is where is it symmetric, and because it's a sine, it's probably symmetric on the y-axis. And once I find where it's symmetric, then I can find the angles that make up half of it and then double the area. So once I get this graphing done, I see what's going on. It's symmetric on both sides. I can start at minus pi over 2 and rotate through positive pi over 2. And that's going to make it a lot easier to solve. So I've got, what I have here is twice the area, right? So 1/2 integral from here to there of our r squared. When I square this out, I've got to FOIL it. So I'm going to get 9 squared minus 9 twice plus the sine squared. Now, when I can integrate this term by term, but this guy right here I have to use power reducing on. So I'm going to combine the 81 and the half, and I'm going to get 162 halves plus a half gives me 163 halves. And then there's my minus a half of the double angle. So you integrate each term. Be very careful. Don't forget that you have to divide by a 2 here, so that ends up being 1/4. Now plugging in the pi over 2, that just gives me a number here. Cosine of pi over 2 is 0, so he's gone. Doubling the pi over 2 gives me pi. Sine of pi is 0. Now I plug in the negative pi over 2, that gives me a number there. This is a 0. Double it, I get 0 there. So the only thing that survives is these guys. So I'm going to get that guy minus a negative of the same thing, which just doubles it and gives me my answer. Okay, we're going to use this same graph on the next problem, but we're going to do the area below the polar axis. Now the polar axis is where your angle equals 0. So what we are actually going to be looking for is the area below the axis. So I can start from minus pi and go to 0, or I can go from pi to 2 pi, 6 of one, half a dozen of the other. Okay, the pole is the origin, the polar axis is the positive x-axis, and wherever that they say theta equals pi over 2, you just see that as the y-axis. All right, find the area below the polar axis of the same thing that we did before. Here's the picture of the bottom of it, and I chose to do double the area from pi to 3 pi over 2. You could do the whole thing and leave the 2 off if you want. You could do 3 pi over 2 to 2 pi. I could have done minus pi to 0. I could have done minus pi over 2 to 0 and doubled it. You can do it however you want to. This is just the way I did it. So I chose to go from pi to 3 pi over 2, and I know it's symmetric. I graphed it, and I can just double the area. So the area is 1/2 the integral of the blob squared. Square it out, use your power reducing just like we already did. The only thing different about this one and the last page is your limits. So I'm going to plug the pi in here, and that's going to give me, I got a common denominator somewhere. Oh, I'm sorry, I'm plugging in 3 pi over 2. There we go. So I multiplied the 163 by 3 and the 2 by 2, and that gave me this ugly guy. And then plugging in 3 pi over 2, the cosine is 0. Doubling that, the sine of 3 pi is 0. Plugging in the pi, I get 163 pi over 2. This is going to be a negative 1 here, so I get minus 18. Then I plug in the pi here and get a 0. So this guy and a minus 18. So I got a common denominator with my pi's and got 163 over 4, and then just got the common denominator with the 18. You could have just left 133 pi over 4 and then a plus 18 out to the side. All right, the homework is going to have a lot of these where you're finding the common interior of two graphs. So you see this is the circle diameter 2 on the y-axis. This is the circle diameter 2, not radius, diameter 2 on the x-axis. So graphing, and I color-coded these. This R1 is blue. When you start at 0, you're at 0, and you rotate through. At pi over 2, you're up here where the sine is 1 and you're doubling it. And then by the time you get to pi, you're back to 0. So pay attention to these angles. We're going from 0 to pi, and that goes all the way around the circle. When we graph 2 cosine, we start at 0, and that puts us out here. When we rotate to pi over 2, we get to 0. And as we finish quadrant 2, we come back where we started. So this is what we're interested in right here. We have to find the angle where those two guys cross. And it'll be the angle where this guy and this guy have the same radius. And you see, excuse me, you see right here, when I'm rotated to pi over 4, my radii are the same value. So at pi over 4, those two circles are going to intersect. And you see they intersect the pole, but they intersect the pole at two different angles. One's at pi over 2, and one of them is at pi. So we have to watch what we're doing here. And very quickly, let's see if this records like this. I'm going to take this little thing right here. We see that each of our guys, the blue one is the sine part, right? And the red is the cosine one. And the blue started here, and when I stopped there, I was done. The red, however, started over here. At 0, he was out here. And then I got to pi over 4, and then went back to 0 at pi over 2. But what we have to integrate is, to find the area, we're going to break this down into sectors. And we've got to focus on, as I'm rotating through the angles, which curve am I touching? So from 0 to pi over 4, I was touching the blue. And then from pi over 4 to pi over 2, each of my sectors has an end point on the red. Do you see that? So I'm going to have two separate integrals that I have to add together. I have to integrate from 0 to pi over 4, the blue guy, and from pi over 4 to pi over 2, the red guy, and add those two areas. And that should give me the common interior. I hope that that recorded when I zoomed in there. That's a pretty picture though, isn't it? Right there, isn't that pretty? Should do that more often. All right, here we go. We're going to integrate R1 from 0 to pi over 4, and then we're going to integrate R2 from pi over 4 to pi over 2. Now we're squaring our R, so that's a 4. That I have to use power reducing. So squaring the 2, pulling it out, and multiplying the half gives me 2 on the outside. Then the power reducing gives me another half. So I'm going to have to factor the half out as well. That's going to make that a 1. And I integrate 1 minus cosine squared, double the angle, and get this. Do the same thing with your constants here, and I get this. Integrate, plug in your numbers, evaluate it, and you get the area that's common to both of the circles. Okay, for some reason my writing got fuzzy. I think I let it sit too long. Kind of like a stale cookie. So, find the area of the interior that is outside the inner loop. You want to be inside the big loop, but not in the little loop. So what we're actually finding here is, let me see if I can highlight this. We're finding this area in here. And I'm not the best grapher, but it's good enough to go by. So when we're doing this problem, we need to figure out what angles give us these points at the pole. I would like to be able to integrate half of the big thing and double it, and then integrate half of the little thing and double that and subtract it out. So what we need to do is graph the whole thing. And you see that at the 0 angle, I'm over here at -9. So I'm at 0, but I'm going backwards to 9. Rotating to pi over 3, I'm still negative. So this guy backs up to right here. Oh, I'm sorry, -9 to here. I was pointing the wrong thing. So from -9, I counted by 3, sorry. Rotated through here, and then once I get to pi over 2, I'm all the way up here at 3. So that gives me a problem. Because I need to know where I cross the pole. If at pi over 3, I'm at -3, and then when I get to pi over 2, I'm at +3, then somewhere in this wedge, I crossed the pole. And you see that if I'm going to do a half of this thing, I'm going to need to know where that is. So what I did was I took that r and set it equal to 0 and solved for theta. And look down here in my cheater box here. I set r equal to 0, solved for the cosine of theta, and got 1/4. So I need the inverse cosine of 1/4, and I don't want to have to carry around either writing the arc cosine or some awful decimal value. So I'm just going to call that alpha, and we'll figure out what he is at the end of the problem. So we're going to say that this guy crossed the pole at alpha. And it's like 0.44 pi. I actually did figure it out. So that's at 0.44 pi, and he was coming from the negative side. So when I started graphing at 0, it came up this way. Here's pi over 3 when I was negative. Then at alpha, I hit the pole, and in this little wedge here, I rolled up to a 3. So from this wedge, I went from 0 to 3, and in this wedge, I went from 3 out here to 9. That would be right here. And you see I blocked it off. Here's where your alpha was. This is the bottom half of the inner loop, from 0 to the pole at alpha. Now I need the inner loop, the outside loop. And from that pole, when I keep graphing, I'm going to be going out to here, okay? So from this alpha out to 15, that's the top loop. But I just want to make sure here, this part was the bottom half of the inner loop. I'd like to have the bottom half of the outer loop just because. It doesn't matter, it's symmetric, you can do what you want. You can go to double the area from 0 to alpha, and then you can double the area from alpha to pi if you want. I chose not to do it that way. I actually got the bottom of the loop, and if you graph this thing and you keep going around, you'll see that your graph starts at 0, goes to pi, comes back to 0. And then if you keep going, you're just going to keep retracing this curlicue thing. So if I go backwards, I can start at minus pi. So the bottom half of the bottom loop is right here. But these are the equivalent. If I take this guy and subtract a whole circle, subtract 2 pi from pi, I can start at minus pi and stop at 2 pi subtracted from that and go all the way to the alpha. It's negative alpha though. It'll be right here. And that'll be where the bottom half of the loop hits the pole. Because at 0, I've rotated through here and I've gone all the way back to 9, negative 9. Okay, it's hard to see it. You got to graph it. You got to just put in the effort. So I chose to get the bottom loop, minus pi to minus alpha. So because it'll be 2 pi minus alpha and 2 pi, or sorry, you know what I mean. So here we go. Set it up. I'm doubling the area, 1/2 the integral of r squared. Same thing here for the outer loop, and I'm going to take the whole thing. Now, this integral is going to give me the whole shebang. This part gives me the part that gets cut out, so that's just subtracted away. So there we go, and the rest is on the next. So I'm going to let this page speak for itself. Double the area. This is what I had set up on the last page. Don't forget, you have to FOIL this out. You can factor the 9 out. Don't forget you have to use a power reducing on your cosine squareds. It's times 16, so the 1/2 makes those 8s. I'm going to combine the 1 here and the 8 here to get a 9, and I'm doing that for both of these integrals. The only difference in the integrals is your limits. And it gets messy. So I'm going to let you work this out on your own so you can stop the video and do the work. Okay, now at the end, once I've integrated everything and I have my answer, I've plugged in alphas into the signs here. So I have to know what's going on, right? The sine of alpha, how are you going to figure that out? Well, alpha was the inverse cosine. So the cosine of alpha is 1 over 4. Pythagorean theorem says the opposite is root 5. And I wrote root 15 everywhere. So I've got root 5 here. So finding the sine, it's just opposite over hypotenuse. Finding the sine of minus alpha, it's just minus the sine. Think about the value of the sine when you rotate forward or you rotate backwards. You're getting the same number, you're just getting the negative of it. Cosine stays the same when you go backwards. So when I have the sine of double the angle, which I have to figure out when I'm plugging things in, it's 2 sine cosine. The sine was this, the cosine was that, multiply it all out, and you get root 5 over 8. Now, the sine of minus 2 alpha would be the opposite of this, minus root 5 over 8. All right, let's get this done. So we're plugging things in. We have 9 alpha plugged in for the 9 pi's. Negative gives me negative. I'm going to let you figure all that out. Just evaluating now. I have sine of alpha right here. So it's going to be minus 8 times root 5 over 4. And that is minus 8 times root 5 over 4. And I had 15s. Sorry. I actually went in and made these 15s because I misread my roots got messy. And I'm not talking about my hair, my square roots. So this is what we end up with. This gives me 2 square roots of 5. This gives me square root of 5 over 2. That gives me 2 square roots. This gives me the root over 2. So that's here. When I combine this guy and this guy, I get minus a whole square root of 5. 2 here is 4, minus a whole. I end up with 3 of those guys. And alpha is just the arc cosine of 1/4. So that's an angle. And there's your answer. Tons of fun, huh? Okay, I know this video is very long, but I'm trying to go as fast as I can. You just stop the video and do the work when I start to get too fast. Okay, arc length is just like before. It's the sum of the squares, but because of the relationships between the parametric equations and the polar type equations, you've got r squared here and the derivative of r squared out here, and that gives you the arc length from the beginning to the end of your sector. When you find the area of a surface of revolution, you have the arc length part, just like we did before, and you have your radius. But if you're rotating about the polar axis, which is just the x-axis, your radius is going to be y. And remember, r sine is the y value, and that's not just the letter r, that is your function, your polar equation here, multiplied by another sine. You're going to have this calculated out, and you integrate. And you see when we go around the y-axis, my x value is the radius. And don't forget your 2 pi. Find the arc length of r equals 2a cosine from minus pi over 4 to plus pi over 4. So we're just integrating from here to there, and this is my function squared and the derivative of the function squared. Notice that I can factor out a 4a squared. That leaves me with just 1. So the square root of 4a squared is just 2a. integrating 2a with respect to theta, I get 2a theta, plug in your numbers, simplify, and it's pretty easy peasy. Okay, next example, 8 times 1 plus cosine on this interval right here. So when I square this, I'm going to get 64, not 16. Isn't this delightful? You get to watch me fix stuff while we talk. So it's 64 here, not 16. And the second guy will also be 64 when I square him out. So when I take the square root of that 64, I'm going to get an 8 on the outside. Well, that was an easy fix. Okay, so I'll correct as I go. That gives me a 64 as well, positive, because it's squared. Pull the 64s out. This FOILed out gives me this, and then I just have the sine squared. And notice that the cosine squared plus the sine squared is going to give me a 1, which combines with this one to give me 2 plus 2 cosine. Factor out that 2, take the square root of it. He pops out to the front, and I end up with 8 square roots of 2 on the outside. Now, integrating the square root of 1 plus cosine is not exactly intuitive here. So, hold on just a second. Okay, how this is done is I'm not going to look at the 1 plus cosine, I'm going to look at the cosine. And I need to use some kind of identity so that I can take the square root of this, whatever's under here. So cosine of theta, if you think about it in terms of theta being double something, then you can take cosine and write it out using a double angle formula, but you're taking half of the angle. You see what I mean? So I choose the 2 cosine squared minus 1 because I have 1 plus in front. These ones will cancel, and I'll be left with just 2 cosine squared of half the angle under the radical. Now taking the square root of the 2 gives me square root of 2. Taking the square root of the cosine of the half gives me cosine of the half. That root 2 can factor out and multiply that root 2 and give me a 16 on the outside. Now, integrating cosine gives me the sine, but the derivative of the angle was 1/2. So I had to multiply by 1/2 to get the du, which means multiplying by 2 to offset it. So this is actually going to give me 32 out front. And let me fix my mistake here. There we go. So in plugging in the pi over 3, taking half of it gives me sine of pi over 6, which is 1/2. Plugging in the 0, sine of 0 is just 0. And there is your final answer. Okay, revolving a curve around an axis. And this curve is given as some number a times the cosine, which is just a circle centered on the x-axis, diameter a. And if you've done your graphing homework, you'll see it. We're rotating this on about the y-axis, but we're only taking this sector of it. So if you think about what this graph looks like, don't laugh. A cosine theta from 0 to pi over 2 gives me this, and this is out here at A. there's the pole, and we're rotating it about the y-axis. So you see what this is going to look like. It's going to be a hump. I tried to take a picture of something in the book and post it, but the picture didn't turn out well either. So you see this is like a, sorry, I keep moving you around there. This is three-dimensional. Don't laugh. I hear you laughing. Yeah, okay, don't show that to anybody. That's what it is. We're rotating it there. We're just taking this curve. So this thing is going to be flat on the bottom. Oh, forget it. I can't draw. It's going to be flat on the bottom and whatever, you get it. So let's do the actual problem here. The area of the surface is 2 pi radius times the arc length is the height of each of those sectors that we're going to be adding together. Our interval is 0 to pi over 2. The radius, because we're rotating on y, is going to be x, but x is r cosine. And the r is the formula a cosine from up here. So this is actually going to be a cosine squared. This thing right here is r squared, so we square the a, square the cosine, and then take the derivative of this, we're going to get negative a sine. When we square that, we get positive a squared sine squared. Missed my square. So factor out the a squared, and you're going to get cosine squared plus sine squared, which is just 1. So that thing is just the square root of a squared, and it gives you this a right here. So I can take the a squared and factor it out and get 2 pi times a squared. But cosine squared, I have to use the power reducing formula. So this is going to be a squared times 1/2 1 plus cosine double angle. So I'm going to factor out the a squared and the half, which is going to give me the 2 pi that was there times a squared over 2. Integrate, I'm going to get theta. This is going to be a sine, but don't forget I need a 1/2, and that's my integral there. Plugging in the pi over 2, I'm going to double it and get sine of pi, which is 0. Plugging in the 0, I get 0. So the only thing that survives is the pi over 2 times this half canceled that 2 right there, and I have another half on the outside, and boom, you're done. Practice it, and I'll send an email about us getting together on Zoom to work some problems together.